Besides my achievements in global geotechnics, like promoting the profession, if I want to market myself or talk about myself, I have a strong experience in design build projects and problems, and now I became, after retiring 5 years ago, a forensic expert in geotechnical engineering and structural a little bit, because you cannot, in my opinion, separate both. So what you see here are pictures of my equipment. I used to own a big company with relatively big, 400 people, piling rigs. I used to drive the machine and drill and do the calculations and the public relations, and so that's my strength as compared to other doctors. I'm not the best in one thing, but I'm good in a bigger range. And I really appreciate your attention, and it's an honor to be here. It's gonna be an interactive lecture where I will learn from you, you will learn from me. We always stay children, especially on this day. And I want you to never grow up. My lecture will be composed of 6 chapters or 5 with some recommendations at the end. And between each chapter, we're gonna have a picture from Lebanon, where I come from, or elsewhere. So how to solve geotechnical problems? It's a philosophical introduction. Review of some theories I think you took already in class about laterally loaded piles under static loads. And my theory that I developed when I was your age regarding laterally loaded piles under dynamic loading. And the beautiful surprise that Scott will appreciate today. And a case history of a project I'm doing right now that is related to the subject. Let's start with SOLG. SO is for soil, L for loads, G for geometry, and H for history. If anybody asks you anything, any question regarding geotechnical or even engineering problem, like give us your opinion on this problem, don't ever answer quick, because a quick answer is related to intuition. You don't want to answer an engineering problem with your intuition. Collect the data, sleep on it, think about it, come back with an answer after you do some calculations and formulate the problem. So collect the soil, what are the parameters, where is the water table, any history in that area with failures or any problems with the neighbors, have cracks, etc. The loads, what are the loads involved? In our case today, we're going to concentrate on laterally loaded structures. And the geometry. Connect with the architect, get the geometry. What are we talking about? Sizes, dimensions, where are the columns? Are they close to each other, far from each other? And it's also related to the load. So they're all interrelated subjects, but you really need to collect all these before you start thinking about your problem. And in my case, I found that it's very, very important to visit the site, especially if you're going to be involved in supervising it, constructing it, or designing it directly with responsibility. If you're designing a project without seeing the site, you are at a lower level than the engineer who's going to be on the site. In terms, lower level means you are restricted imagining things that may not be there or cannot be implemented, especially if you become international. Like you cannot design a project in Nigeria like we're going to see today if you're sitting in Texas. It's better to go there. The trip Even if you want to pay from your own money, if you're going to take responsibility, it's better to go there and visit the site. And your design will be much better, believe me. So Soldier Stage 2 is, after you collect the data, then you sleep on it and you start thinking, what are the modes of failure that are controlling? Like, how is this going to fail? Where is the most critical thing that may happen? Because if you don't know how is the mode of failure, which theory are you going to use? You cannot tell which theory, which formula, which software, which... You have to know how is this going to fail. Is it going to fail by structural breaking, or it's going to fail because the soil is going to heave, or it's going to fail because you have high water pressure? So what are the applicable theories, which software to use? And then comes the triangle, the famous stable triangle of the engineering mind. So you always think of safety, yes, but also cost, because you can be very safe and super expensive and they'll kick you out. And functionality, you want it to work. So this is where your engineering calculations come, and once the calculations are out, you make your judgment. And if you have many software, use them all, because you want to make sure that they're all kind of compatible, get you closer to some logical results. And if they are way apart, use a third method, fourth method, as many methods as you can. And also, never forget hand calculations. If it's a very complicated problem, simplify it and check by hand. Check by hand, your mind has to complement the software. Finally, stage 3, and this is where I found 80% of problems in engineering come from units, compatibility of units. Once you have the output, check, is it logical? Are the units compatible? Even in the software, you may enter the moment in ton meter, the pressure in megapascal, and then the whole scenario is messed up. Just to tell you that this is true not only in geotech, because 10 milliliters of antibiotic can save your children. These are my kiddos when I was younger. But if you change the unit and give them 10 liters, this can kill an elephant. Units, never, ever forget the units. Never. I've seen catastrophes. Okay, back to our subject. So when I change from, because we are a small audience, from one chapter to another, you can interrupt me between those two chapters if you have a question from what passed before. My dear friend. So we're going to start with the subject of today. If you look here, you see two similar piles. One is loaded laterally and the other vertically. Can we add the results, like separate the two conditions? Because vertical loaded piles have set theory and laterally loaded piles has another set of theory. Can we connect them together? In reality, you cannot, because soil is not an elastic medium. You cannot just say this force plus this force, we add the movement and deflections. That's not true. But what is saving us in piles is the fact that when you load the pile laterally, you are involving the top layers of the soil. 1 times diameter, 2 times diameter, 3 times diameter, depending on the soil, and maybe 4 times diameter in soft material. And the vertically loaded piles are involving the lower layers. So then adding them to get the real answer is okay. In my opinion and practice, it is okay. Now there are theories where they combine both with the P delta effect, but it's too complicated for real life. So today we're going to concentrate on laterally loaded piles. And probably, I think from what I heard from Dr. Ballouz, that you already covered the two theories for flexible piles, rigid piles. Did you do that in classroom? Yeah? So what separates them is what we call the transfer length, which is an interactive parameter between EI. EI are for the structure of the pile, modulus and inertia of the pile, and K is for the soil. Soil representing the soil. The ratio 4/√2 gives you a transfer length. If the length of the pile is less than L0, you have to do the rigid pile theory. If the length is more than 3 times L0, the pile becomes flexible. And we will see what is flexible. What do you do in between? What the teachers told us, and maybe your teachers too, if you are between L rigid and flexible, L less than L0 and L more than 3, what if you are L 2L0, equal to 2L0? The teacher will tell you, it's your decision. Do some interpolation, use your judgment. Are you closer to rigid, closer to flexible? And this is the big surprise that I will tell you later. What is the missing link? What happens in between? That's why I am here. Back to the theory of the laterally loaded piles. The design aspects, the major ones, are Y0, which is the deflection at the top. You want to limit it between 5 and 20 millimeter, so maybe 1 inch in most cases. Sometimes you can go higher if there are no lives involved, if there is no big loss involved, you can make it deflect more. Also, you can allow higher deflections if the pile is sticking above the ground. And you're controlling the structural strength better. Y prime 0 is related to that. You want to limit it to 0.5 to 2 degrees. You don't want it leaning too much. But again, it's all depends on you. There is no code. And I don't believe too much in codes, actually. I believe in the engineering mind. Codes are made for those who are worried to make sure they don't go to jail. But it limits you, really. There is a fourth code, which is your brain. If you can prove it, you can calculate it, go for it. Whoever wrote the code may not be smarter than you. He's just protecting you a little bit. And sometimes it doesn't apply to the case you have. And this is an important thing. The maximum moment should be less or equal to the allowable moment that the structure can take or the pile can take, which is not the case in vertically loaded piles. The vertically loaded piles most often break from the soil breaks, that gives in. It settles more than you want. In laterally loaded piles, the pile breaks before the soil gives up. Some theory here. I don't want to dwell too much on the theory, but the way it was developed, you take a discrete element, dz, and then you look at the constitutive equations and the equilibrium equations. So you have the moment is related to radius of curvature, which is in turn is second derivative of y with respect to dz. The py curve is, you have to imagine that the soil can be a spring or represented by a spring, which has a k constant. So these are two equations from the constitutive equation. Then you look at the equilibrium equations. If you look here, the sum of forces in the horizontal direction, V plus dV, P dz, because pressure times the height should be 0, and then the sum of moment around the center should be 0. So M plus dm is turning this way, minus M, opposite, minus V dz, opposite, plus V plus, or minus V plus dV, also in this direction. So sum of moment equals 0, and you get 2 extra equations. Putting all these together will lead to the governing differential equation that we need to solve. So we take that governing differential equation and, oh, before I jump to that, the solution. I'm listing here some typical values of K for the spring, in case you want to take a snapshot, because it will help you, give you some range of results. It's for guidance only. So back to the differential equation. If you assume a solution of a general form and you put boundary conditions, we reach what is the flexible pile behavior, or the flexible pile theory, to predict the lateral deformation with the depth z, having moment at the top m0 and h0. So for any moment m0 and h0, if you know K of the soil, the EI of the pile, you can predict the deformation of the pile. And this, if you keep going, derivatives, you get here the slope, and you keep going, you get moment and shear. Second derivative, third derivative. Now for the rigid pile, if the pile is now rigid, you lose one equation because R can go to 1 over R can go to infinity, or does not exist. But now you have from the geometry that yz equal rz plus s. It's a straight line. And applying boundary conditions, you reach the rigid pile equation, or the behavior. So for any mz, m0, h0, k, and the length, you can get how much deformation you have per depth if the pile is rigid. Are we okay so far? I went through this quickly because you were supposed to have this. Some theory change a little bit, but they all come from the same concept. Like you may not have the same nominations or factors, but they follow the same rule of discrete elements and the spring Py curves. What I'm showing you here, I did this when I was giving a lecture, I forgot somewhere, I think in Korea. I went to the supermarket and got a water bottle and filled it with sand, and did the same thing, filled it with mayonnaise. And I used the same straw. So the same straw in mayonnaise behaved as a rigid pile. You can see the tip of it here. And in this picture, you can see how it flexed. So this is the soil structure interaction. You have to feel it to understand it. And what we're going to do now is the same exercise in a different way. So each one of you, take a pen or his pencil and grab it like you see in the picture. And I'll take one too. Maybe I can take the mic, which is a solid pile. So we're grabbing the pile like this, and each finger is actually your soil finite element or discrete element. So your fingers are representing the soil. The pen or pencil is your pile. The embedment is where your fingers, top and bottom, are touching, and you apply a lateral load. And what you feel is the K constant. This K, if you are not strong enough, you don't do bodybuilding, you'll have a rigid pile deformation. But if you're strong and you eat lentil soup, you can actually bend that pen like this. You see the flexible pile? Can you see the flexible pile? I eat lentil soup. So this is the same thing, rigid pile. I cannot bend the pile. It's rigid, the deformation is, that's exactly what happens in the field. Exactly this. Don't forget that. Always feel it. So you look here, the load is at the top, you're applying, your fingers are K, your pen is EI, and L0 is this distance. Are we on the same page? Any question? Let's keep going. New chapter, this is to change your mind. This is the valley of Qadisha in Lebanon. Lebanon is mountains by the Mediterranean, a lot of snow, a lot of rivers, and this valley is what we call the Holy Valley. And it's a World Heritage United Nations Valley. Have you been there? Yes?
It's all right.
This is the village of Pshari. So now, the theory I developed when I was your age. How did it start? It started on a chair. So I was sitting like this. Of course, my shoulders were very shy, and the professor was there. And I said, I don't know what is my subject. I want to graduate in 2 years. And Dr. Brio was there, said, stand up. So I stood up. He said, bang on the chair vertical. That's it. And he said, is it glued to the floor? I said, I don't know if you glued it last night. I don't think so. He said, bang the same way, same force, lateral. And he said, is it glued to the floor? I said, no. He said, the lateral wave will show us more information in the pile than what everybody's developing with the compressive wave. Do you agree? I said, yes. He said, okay, go solve it. And it took me 3 years to figure it out. And by the time I finished, the paper was nominated Best Paper of the Year. And that's what I'm going to show you. So when you start with dynamics, because we developed it on the dynamic loading, when you start with dynamics, the governing differential equation, which is actually like an equilibrium equation, will have a couple of extra factors. Remember, the governing differential equation before was this number, and plus ky equals 0. Now we're adding the mass times acceleration plus the constant k of the dashpot times velocity. And the solution to this differential equation will give us, under dynamics, something very nice and very long that I'm going to show you, like from the, it's not a snake, don't be worried here, but it looks like a snake. I'm going to need your help. I'm going to start from here, or maybe from here. Are you busy?
Always.
So we're going to start unrolling this back and forth and back And this, what you're seeing here, is the solution to the differential equation. And the formula that I typed on font 16, that give me some more room, is actually 110 feet long. I don't know it will fit here, even back and forth. Yes. And why is it funny? Because we're being recorded. So y as a function of z and t, y as a function of z and t is the solution. So at any depth z and at any time t, if you let the software calculate this formula, it will give you 1 point. So at any time, and any depth z and any time t, you get one deformation. Imagine this is happening in an earthquake. So when you have an earthquake, you have, and that's what we're going to see on the, yeah, it's okay. You can look at it actually. It's a lot of fun. Somewhere, who can see plus m0? Because
it was over there.
it's f0 plus m0. So from here all the way to here is what's related to the force, and then what's related to the moment. If you don't have a moment, we can cut it in half. And remember, this is for K constant. So this is a homogeneous soil. If K is a factor of depth, then the differentiation and the integrals will give you a formula that is 16 to 32 times longer. Can you feel that? Okay, now keep holding it 1 second. We're being recorded. You can smile to the camera. And this is what happens. And look at the radians per second. This is the wave that's moving the pile 15 millimeters, so this much. If you go faster, with a faster frequency, it will not go that far, because by the time you reach 15 millimeter, the force is bringing it back. So it goes 10 back, and higher frequencies are safer in earthquakes than lower frequencies. Why structures fail when they are on clay? Because the wave comes, and let's say it's transmitting from the rock at high frequency, and then hits the clay, it becomes high amplitude, it amplifies. So you want to keep this in mind, and you can feel it using this software. So we can roll it back. Let me do this so that we don't break it. My formula! I love it. I'll go fast, and then I'll let you take over. Carefully. Another chapter, this is another picture. Probably you can see at this time, what time is it in Lebanon? 8 o'clock? This is in the Cedar Mountain. So it's at sunset. Did you know that it snowed all weekend? It's amazing. We never saw this in end of April. The whole mountain is full of snow now.
Sorry.
Thank you, doctor. It's gonna smell good now. Can you help, doctor?
Let me take it.
Yes. We don't want to bend it. Yeah. Now this is the fun part, the missing link. I'm gonna take a break from PowerPoint and go to Excel. So here I have three columns: the rigid pile theory, flexible pile theory, and the new theory that you just held. So if that equation I put a very slow motion or a very slow frequency, it should collapse onto the static loading theory. Will it collapse onto the rigid one or the flexible one? And this is where the formula was beautiful, because it collapsed on both. It collapsed on the rigid one if L is less than L0. It collapsed on the flexible one when L was more than 3L0, and it showed us what's in between. And it proved that what's in between is not an interpolation. And what we've been taught in classrooms is wrong. So, and this is news to you. Scott, Hashash, did you hear what I said? So, if you take, for example, the diameter here, can you follow me, is 1.5 meter. The moment, and this is an actual case study that I'm doing now in Nigeria. So if you take that 1.5 meter diameter pile, same soil, which is here, K, dense sand, and I put 0.5, it's more flexible. It flexes more. The deflection is 8 centimeters, so 80 millimeter. The riser means the distance of the pile above ground. Let's put 1 meter for now. If you make that soil mayonnaise with the same pile, so I put 10 megapascal, it's not rigid yet. Let's go back to 1.5 meter. You see that the pile is here. The pile is 12 meters, and now it's somewhere in between 6 and 20, 3L0. So L0 is 6 meters, 3L0, 20. Look at the red line. Look at the surprise. Look, the deformation is more than both theories. So if you interpolate between both, you are wrong. And the y prime 0, the deflection is all, the angle at the top is also given here. If we make a short pile, let's say 6 meters, look how the red line collapses now onto the blue line. So the equation I developed when I was your age collapsed and matched both theories. And we were very, very happy to discover this. And now I use it all the time. Whenever I have laterally loaded piles, I start with it. It gives me a feeling of strength. I'm happy with it. Why? Because it's a mathematical closed form solution, which is very solid. When you solve mathematically something, you are always right. Now we're going to jump to this picture. This is south of Lagos in Nigeria. It's an aerial photograph showing an existing industrial port for the largest refinery in the world. And this is where our project is going to be. Yes?
This is the part where we can make questions.
Yeah.
Okay, perfect. So it was pretty fun about the equation. Actually, it's really long. It makes sense because it's actually a dynamic solution. So my question is, this solution that you show us, it's for a dynamic load applied in the head of a single pile as a time history, which is like pretty much like acceleration versus time.
No, it's you have to put the intensity and the frequency. It's cyclic.
Okay, so it's like a static.
It's
Sorry, it's like a monotonic.
monotonic.
Dynamic
It's a wave. It's a wave action. Yes.
Okay, perfect. So you did that to simulate an earthquake action?
No, I did that as part of my research to discover anomalies in piles.
Okay.
But I took a portion of my research related to laterally loaded piles to show you the missing link. But when I developed it, it was more to develop a non-destructive test. Do you know how they hit with the hammer the
For the
pile?
wave equation, yeah.
Yes, use the wave equation to see if there are anomalies and the wave, the shape of. I did the same with lateral, and we were able to predict the capacity of the pile lateral and predict the static capacity. But that's another section of the research.
So actually my question was like towards that. So with this method I can determine the static
Capacity.
lateral capacity.
Yes.
No
The big K.
No the earthquake response.
Not really,
Okay.
because the earthquake comes with variable frequencies. You can play with it, like change the frequencies as I showed you, and see how it changes, and be able to determine the peak frequency.
I was thinking you can actually do like a model analysis.
Yes,
or
you
separating
can.
model.
If
with
you write the
line.
software with the variable frequency, you can do that. You can see how the pile moves and then how it goes higher and then high faster, but it's not too much movement. So you can determine what is the worst frequency if it hits this pile.
Thank you.
Did I answer?
Yes.
So the extension of this port in orange is what we're going to be designing as a jetty subjected to lateral loads. And the blue zone will be dredged. You know what's dredging? It will be excavated. So the water will go in and big ships, 300-meter long ships can go in, like this yellow one. The location is kind of diametrically opposite from the Earth. So we are on the top is Urbana Champain. The project is in Africa, southern Nigeria, in the city of Lagos, which is the largest city in Nigeria. Not the capital, but the largest city. I'm going to show you here what is dredging, and this is how they're going to... The dredger sucks water and sand, takes it in the ship, and dumps it somewhere else. So we're going to be... That's an overview of the site. I'm taking the movie, and this whole area will be dredged. These are pipelines, and this is where the jetty will be, where I'm showing with my finger.
This is where the port will be. Extension.
All the way to my feet. All this will be water. Is it clear now? Always visit the site, it's beautiful. So that's a picture. I'm showing where the jetty will be and where the water will be in this direction. And the top view layout, it's now clear to you, right? I was sitting right here, standing right here and taking, actually I was standing here with the video here for the picture. Okay? And all this area will become water and big ships are gonna be here. Now for you to know, I'll show you so you can visualize the weight that is involved. But let's start with the soil. Solgi, remember? So we go back to the soil data. Look at the SPT values. Upper 30s. And these are pretty good values for sand by the ocean. Do you have any idea what's the bearing capacity if you have N? Quick rule of thumb, you divide by 9, and that's your allowable bearing capacity for a spread footing in TSF, or kilogram per centimeter square. So N divide by 9, I use it all the time to impress people in the site, on site. So if you are 30, SPT is 30, divide by 10, you can put 30 tons per square foot. That's a pretty good soil, safely, with about half-inch settlement expected. On the surface, if you go deeper, it's better. You remember the formula, CNC plus QNQ plus 1/2 gamma BN gamma, which by the way is a wrong formula, but we used it for so many years with many correction factors. So some geometry here, and the loads, look at the loads. You have 100 ton per bollard. The bollard is where you tie the boat. And this, there is every 22 meter one bollard. You have 15 ton per square meter. That's a lot of spread load. And 40 ton per linear meter coming from the earth pressure. And some more data about the geometry. This is how the piles are going to be. Front row piles, four rows, 1.5 meter diameter. The back rows, 1.2 meter diameter. Spacing between them, 5.5 meter, and the longitudinal or in the direction parallel to the ocean. And then in perpendicularly, it goes from 6 to 4.2 meters. You can see it on the left side. The whole jetty project, 440 meter long by 40 meter wide. You can see it here. 40 meter wide, and it goes 440 meter long. Is this clear? Yes, it's pretty colorful. Just to give you an idea about the loads we are talking about. This is the largest reactor, one of the largest in the world. Take a closer look. You see it? The car here? This is how big this load is. Other high loads are the cranes. This is one of the risers that were downloaded onto the jetty. And that's another aerial picture of the ships that are expected. And the 100 ton per bollard, you can see from the ropes here. These will pull in case they hit on the fenders or there's a wave action. Lateral, expected maximum lateral push or pull is 100 ton per bollard. Geotechnical analysis, I use the NSoft group as one software. This is the 3D model with the soil layers that we have. And the deformation expected here is about 6.6 centimeters or 66 millimeters. And when I did another analysis with Plaxis, you see the deformation, how it's going to move laterally and some bending on the secant pile wall in the back. And the movement, when I discovered that 6 and 6 are very close, I was very happy. Actually, I was surprised because this is very rare to have match like that. 6.6 and 6.3 centimeter using two different software. Now structural, something you like to hear about. How do you go from the geotech analysis to the structural analysis? You can have one software that can do both. Russians are good in that, but it's so complicated to put all the data. you can go from the superstructure to the underground in one software. Rare are those softwares. I know some good Russian software, but I like to divide the two and go from the geotech to the structure with the loads inserted at the joints. Like here, the slab, to do the structural analysis of the slab, I put the slab on flexible joint, and I apply the moment that I saw on the pile tops from the geotech software, I apply it at the node. And I keep all of them rollers as rollers except from the front row. That's one way. Another way to do it is to make the structure with the pile that extends to the point of inflection, where the moment is zero, and put a roller there, a simple support. That's another way of doing it. And by doing so, you get the moment diagrams for a section that is 22 meter long, because this is 440 meter long jetty, but it's easier to divide it in 22 meters, because every 22 meters we have one bollard. So it's repetitive. You analyze it in 3D, but it's modular 3D. So this is the moment diagram in the Y direction and the X direction, shear diagram in the other direction, shear diagram. And here I want to open a parenthesis. Correct me if I'm wrong. Whenever you have a solid slab, don't worry about shear. Worry more about moments, because to break a solid slab in shear, you need very high loads, concentrated loads. To have punching, maybe. So I checked shear here, and we are very safe, even with all this high loads, 15 tons per square meter. Moments in the slab portion, because the slab is designed as a waffle slab with beams in both directions that are 120 centimeter high, or 1.2 meter beams, and the slab on top is 50 centimeter or 500 or 0.5 meter. So what you see here is the moment distribution in the slab in the direction parallel to the ocean. And this is the other direction, perpendicular to the ocean. You see in red the negative moment on top of the beams, and in blue the positive moment in the middle of the slab. You have to satisfy this. This is how you determine how much steel you need in the slab, or if it's too much steel, you make it thicker, etc. If the steel is provided by the client and you are the contractor, you make the slab thinner to gain more money, etc. These are contracting tricks. So once you get all the moments and shear stresses, etc., you can now do your structural drawings. At this point, I'm going to conclude with some recommendations. How am I doing on time? Do I get another chocolate?
You're good.
Do we have time left for some interactive discussions?
Yeah.
How much time
The
left?
end of your presentation.
Huh?
We have 15 minutes for the class. And
Oh, good.
Class ends, yeah.
I was worried I went a bit fast, but I think we're good. Maybe I can show you another case history. So recommendations. Remember, wake up. We gather. Gabriel, you're okay? You need coffee? We gather all the data before giving any answer. Apply all possible theories. Use your judgment. And check the units. That's Solji. Don't rely on intuition. Can I have one piece of paper?
Yes, sir.
Don't rely on intuition. So if you take this piece of paper and you bend it 1 time, 2 times, 3 times, it's becoming thicker, right? If we bend it 50 times, how thick will it be? I'm going to give you 4 possibilities. You use your intuition, and then we're going to do it mathematically. First is 1 inch. First answer. Second answer is 10 inches. Third answer is 1 foot. No, 1 foot is like 10 feet. 10 feet. So 1 inch, 10 inches, 10 feet, or you reach the moon. By intuition, what would you answer?
I think it's impossible to bend it 50 times.
Impossible to bend it 50 times. If it's a huge paper, you can, no? Like, imagine you can.
Okay.
Like, this is 0.2 millimeter. I mean, your intuition would say how much? Maybe 10 inches? 1 inch? 10 inches?
Like 1 inch.
1 inch? It's okay, don't be shy. I mean, we're all going to say a wrong answer.
I don't know.
Actually, you reach the moon. Put it in your calculator. 0.2 millimeter times 2 to the factor to the power 50. 0.2 millimeter times 2 to the power 50. You will reach the moon. So never ever use your intuition. In engineering, always calculate. You want another fun problem? If you have a rope and you release it from here to go all the way around Earth, all the way and come back, like we did with my formula, all the way around Earth, touching the surface of the globe, and coming back to my hands, tight around the globe. Okay? And now you make it 6 meters longer, grab the new end, put the 2 ends together, release it equally all around Earth. The rope is now like a belt, right? It's not tight anymore. How high will it go above the ground? By intuition. So it's 6 meters long all the way around the Earth. By intuition, will it go, will you see it go higher? Any answer?
You wouldn't even notice.
Microscopic? Negligible? High?
2 pi r.
Yeah, so let's do it mathematically. Let's do it. You want to do it mathematically? You will be surprised.
It's more than you think.
It says more than you think.
Yeah.
So you have the radius, first radius is the radius of the Earth. The perimeter is, what's the perimeter of 2 pi r? And the second radius is 2 pi r2. We want r2 minus r1, which is the height, right? So 2 pi r2 equal 2 pi r1 plus 6 meters. Correct? Can you write it down? 2 pi r2 equal 2 pi r1 plus 6 meters. Can you find for me r2 minus r1? So you can start by dividing by 2 pi both sides. Yes. Both sides. Divide.
1 meter.
Divide by 2 pi. 6 by 2 pi. Yes, how much is that? It will be close to 1 meter. See how simple? Why you don't want to do it by calculate? It's so fast. Never ever rely on intuition. You are engineers, not poets. So, innovate if needed. If you have a problem with many variables, I would love to take you out to this beautiful excavation. It's actually one of my expertise. shoring deep excavations. I have a webinar on this. Recorded, you can access it for free on the ISSMG website. So innovate if needed without compromising safety, and don't follow the code blindfoldedly. Be innovative. Stay involved with your project. That's what we're gonna do between me and this department regarding the jetty, and we're gonna monitor it and write papers on it and see if the calculations you saw, which are still at the early stage, you're gonna do in the department further calculations, further analysis, and see how the monitoring long term is gonna compare to the theory. And this will be your best continuing education in life. Once you start working in Langen, who's going to Langen? You? Yeah. Try to stay involved. Even if give you another project, call the guy you worked with a year ago. Say, hey, how is the project going? Can I visit you? I'm going to San Francisco, have a drink. Tell me about it. This is how you learn from what you designed a year before. How it's behaving. Did you see any cracks? Or did you see, is it over-designed? Most of the time you learn from over-design. You start taking more risks to become more accurate and more precise and more famous. You become famous when you save money, not when you do beautiful theories. When you save the client money, he's gonna tell about you. Oh, this guy has saved me tons of money. And you may become, I'm not gonna say, drunk. You may become drunk and you take more risk, and then you fall in a big catastrophe. You learn more, like happened to me. I have many failures under my belt. Don't think that's how I learn. So all of this is because our profession is beautiful. Thank you very much. I'm going to leave you with this picture that I took a week ago from the Lebanese mountains. I'm still alive. And wait, one more slide. Then the most important. Thank you very much.
Well, thank you so much for the very beautiful presentation. Do you guys have any questions for Marc?
Yes.
Yes. Sorry to keep bothering you with.
Don't worry.